Hola amigos, ¿qué onda? Welcome back. In this video, we're going to define nodes of a circuit. Before we do so, I want to formally introduce the definition of a circuit for our work. We say that a circuit is a set of elements in which each lead of those elements is connected to the lead of at least one other element. In a very, very basic example with two elements, we would say that a circuit exists when we connect the leads. We could actually create a circuit out of a single current source and a single resistor by literally electrically connecting these leads together. Generally, when we're doing electronics, we don't want to use our hands as connection pieces, and that's where the concept of using breadboards come in. But the moment that those pieces of metal are connected, that creates a circuit. When we break those pieces of metal apart, when we create an open circuit, no longer are those electrically connected, so electrons cannot flow through thin air, and we say that that is not a circuit. In another example of what circuits look like, on the left-hand side in this diagram, we see a three-element circuit. Because each lead of these elements are connected to the other leads, it completes the loop, and electrons can flow freely from element to element. Over here, we see that this is actually not a circuit because we have these floating leads on the bottom. Specifically, the bottom lead of this left element is connected to no other element. So too is the bottom lead of the right element. This does not form a circuit. We can actually take a look at a specific example of such a circuit. So in this situation, we have a voltage source over on the left. We've got a resistor up top, we've got a resistor on the bottom, and then we just have a single conductor running along the bottom part of this circuit. In the case that all of the leads are connected together, we would say that that completes a circuit, which you see over in this situation. If I were to take this bottom wire out, no longer is the bottom wire of my voltage source connected to the other portion of this resistor, and this is actually not a circuit because we have this floating lead. The same thing would happen if I put the bottom of the resistor into a contact strip that is not actually connected to where I connect my other components. Even though that resistor is in the breadboard, that has no electrical connection. Now I could fix that really, really easily by just putting a jumper wire in between and making the connection between where the resistor is and the contact strip that's connected to the other ones, just like that, and I push it down, that would complete that connection. But unless I very specifically make sure that each of the leads lines up with the other ones, I actually don't create a circuit. One of the fundamental assumptions that we're going to use when we design, build, and analyze circuits is that the size and shape of the leads has no effect on the electrical behavior of the actual circuit. This means we can stretch, deform, bend, do whatever we would like with the wires in our ideal circuit diagram. One of the things that I really love to talk about is not only the mathematical assumptions that we're using to build the ideal models, but why that actually works out. And the reason is, in my circuit, I can create the exact same mathematical structure by just changing the connectivity like this. I've taken series resistors and just deformed the lead. Instead of these leads being connected through contact strips in row 10, they are now connected through contact strips in row 2 with a jumper cable, and the jumper acts as an extension of that wire. And that is why when we're looking at the ideal elements, I can bend and manipulate and stretch and compress or whatever I would like, because I have the options of adding wires or taking out wires or literally bending and deforming. Like I could do that to my resistor and I could do this to my resistor. It doesn't change the electrical connectivity. All that changes is actually the physical structure of that. That will matter when you're creating printed circuit boards. One of the things that's really interesting is that size and shape actually have an effect on the way that circuit board is laid out. But in terms of the actual underlying structure, the electronics behind that, we assume those don't matter, and that's why. With this in mind, we're going to say that the only information that governs the behavior of our circuit as we analyze to figure out what's going on with the circuit, the most important pieces of information are the features of each element in the circuit, and then how are they connected together. When we talk about how elements are connected, that is called the topology. When we talk about the features of each element, we're going to call that the current versus voltage relationship. Sometimes these are called branch constitutive relationships, which we'll get into. The linear algebraic nodal analysis algorithm captures circuit topology as incidence matrix of the corresponding directed graph. Don't worry about any of that formal technology, but the idea is the only two things that matter are connectivity and circuit behavior. We're going to capture connectivity using matrices. We're going to capture circuit behavior using matrices to express mathematical equations. As a recap, when we say the topology of a circuit, we mean how the leads of the circuit are interconnected. To determine circuit topology, we will look at whether or not any given lead is connected to another lead of any element. We say that the circuit topology of any circuit is completely determined by the nodes of the circuit. And we've mentioned nodes previously, but because circuit topology, because the interconnectivity between elements is so important, I think we should give a formal, rigorous definition of what nodes are. Towards that goal, we're going to define the nodes of a circuit as the connected segments of conductor, the pieces of wire that are touching each other, that sit between the bodies of our elements. Yuck, that's a lot of words. Let's actually dissect what those words mean in terms of looking at a schematic and then making the relationship between that schematic and an actual physical real circuit. Quick recall from a previous video, we said that for an ideal element, we call this a lead, body, lead. We're calling the nodes the connected segments of conductor, the connected parts of leads that sit between the bodies. We're going to define the node identification heuristic, the thing that we're going to do to try to find where these nodes are, as follows. If I want to know where the nodes are, what I can do is erase or white out the bodies of each element. So here's the body of the voltage source 1, here's body of resistor 1, here's body of resistor 2. Let's go ahead and white those out and then see what's left over. We've defined the nodes of the circuit as the connected segments of wires. We've said that in order to identify those, we erase the bodies of each element, and then the corresponding pieces of wire, the leads that are connected, are our nodes. Here we see those two leads are connected. That is a single node. Here we're going to see a second set of leads that are connected, and that is a single node. And third, we see that the leads down here, the left lead over here, and then the right lead or the bottom lead of the right element, those are connected. And we're going to say we've got 1, 2, 3 nodes. I am going to label or enumerate the nodes using just integers. We're going to reserve labeling nodes with variables and letters for when we actually want to measure a property of the nodes. We're going to call that node 1. We're going to call that node 2, and we're going to call that node 3. Once we use our heuristic to identify where the nodes are, we can label those in the schematic, and then we can make a direct comparison between what's happening in our circuit schematic and what's happening in our actual circuit. In this situation, check this out. This set of wires right here is all one node. It's all one kind of connected segment of conductors, and that happens right here. The entire red wire under in that contact strip, and then this piece of metal on the left hand side of my resistor, all of those are a single node. If I wanted to put the positive lead of my multimeter, I could put that anywhere along that wire. Now, the actual conductor inside that voltage source wire is not shown, but if I just strip the darn thing, inside there's that wire. Check this out. Now, literally all of that wire underneath in this contact strip, that's all node 1. When I look at node 2, it's the entire right-hand piece of wire on that resistor. I've got this piece of wire, this lead right here on the upper part of the body of that resistor, and then the contact strip. So that's all node 2. I could connect my multimeter anywhere along any of those pieces of wires and it would be the same node. And then down here, the electrical connection literally runs all the way down on this piece of wire, through the contact strip, through the jumper wire, through that contact strip, through this black wire together. That's how we identify node using the node heuristic. Remember, we're going to think about the nodes as the connected segment of conductor, the connected wires, the connected leads that remain after we erase the element body. If I ever want to identify nodes, I just erase the element bodies. Let's test this algorithm out on a much more advanced circuit that we're going to use later in our process of developing the linear algebraic nodal analysis. This is a circuit that has 8 resistors. Resistor 1, 2, 3, 4, 5, 6, 7, 8. It has 2 voltage sources, voltage source 1 and voltage source 2, and it has 2 current sources. In order to identify the nodes, remember the nodes are the connected segments of wires after I erase the element bodies, I need to erase all of these bodies and see what's left over. Now I'm going to be a little bit magic. Ready, steady, go. I can erase those element bodies and check that out. The nodes that are left over are the segments of wires that are there. I'm going to go ahead and color code these for you so that you can make a distinct connection between what's happening in the node heuristic and the actual physical circuit. Here we are. When we cut out the element bodies of the first 2 resistors, we see that this little segment of wire is left over, that blue segment, we're going to call that node 1. When I cut out all of these element bodies, we see we'll call that node 2, 3, 4, 5 in red, 6 in purple, 7 in orange. Now, as we get more sophisticated, we're going to actually play with this wiring diagram that you see on screen, and we're going to build that. For the purposes of this video, I have done that for you prior to working with this. Don't worry, we will get into this. But what I wanted to show you was the nodes of the circuit correspond with actual segments of conductor. If I wanted to see this little pink T, that would actually be all of the connective pieces in between resistors 4, 5, and 7. That is this set of metal. I could connect my multimeter anywhere on that set of metal, and that would give me access to node 3 that's highlighted in pink in that schematic. To recapitulate, the nodes of a circuit are the connected segments of wire that sit between the bodies. Nodes completely determine circuit topology. What I mean by that is when I'm looking at this circuit, I actually don't know what elements are inside of those. I could think about those like black boxes. The actual circuit behavior matters, but that's not what's captured in the nodes. What's captured in the nodes is how are the elements connected? And we'll see this when we're going to design an entire incidence matrix. We're going to design a way to capture all of the connectivity as a matrix with integer coefficients. That matrix will tell us how one element is connected to another element. Then we'll use the mathematical model for each individual circuit component that we discussed in our last video to start bringing some refined view of how those elements interact with each other through electrical behaviors governed by mathematical models. With that, we've defined what canonical circuit elements look like. We've got a schematic, we've got mathematical models. We've defined the underlying terminology, which is called nodes, to talk about how circuits are connected. In the next set of videos, we're going to do some data collection on some slightly more advanced circuits that require a little bit more technology to fully understand so that we can set up our discovery of both Ohm's law and Kirchhoff's voltage law and Kirchhoff's current law. The most unique piece of our approach here is that all of our paradigms are going to be through matrices. The standard approach to most of this is to do it in scalar space. And I am making a claim that while that is great for introductory material, it actually separates 2 ideas that I think should be connected together. How does linear algebra show up in its client disciplines? And then how can we use linear algebra to simplify systems thinking? Scalar thinking is very, very good when we want to focus in on one individual element, but what if we wanted to capture the entire dynamics in one set of equations? Dun, dun, dun. Here comes linear algebra. See you in the next video.